Imagine a world where a child's mysterious symptoms, something no doctor has seen before, could be diagnosed in days, not years. That's the promise of a groundbreaking AI framework, reshaping rare disease diagnosis. Today, we're diving deep into how this system works, why it's a game changer, and what it means for patients worldwide. Let's start with the problem. Rare diseases, defined as conditions affecting fewer than 200,000 people, impact 350 million globally. But here's the catch: traditional medical AI struggles. Why? These models rely on static training data, which can't keep up with the rapid pace of rare disease research. New mutations, emerging treatments, and evolving classifications mean doctors often face a knowledge gap when diagnosing these conditions. It's like trying to solve a puzzle with missing pieces and a constantly changing image. Enter a two-part system designed to bridge this gap: multi-granularity concept activation and a hierarchical knowledge graph. Think of it as a supercharged diagnostic assistant that thinks like a human expert but scales like a machine. Let's break down the first component: multi-granularity concept activation. This isn't just one-size-fits-all reasoning. Instead, it analyzes rare disease clues at multiple levels, like a detective using different magnifying glasses. For example, if a patient presents with episodic ataxia, the system doesn't just search for that exact term. It also explores exact matches, direct symptom or gene name references, semantic variations, related terms like movement disorders or neurological instability, taxonomic hierarchies, linking the condition to broader disease categories, e.g., channelopathies, cultural linguistic nuances, accounting for regional terminology or historical case studies. This multi-layered approach is powered by 4 specialized algorithms, each tuned to a different granularity of data. But here's the twist: a diversity control mechanism ensures the system doesn't get stuck in echo chambers. If one algorithm keeps returning the same answer, the system actively seeks alternative explanations, like a brainstorming session where no idea is too outlandish. Now let's talk about the second pillar, the hierarchical knowledge graph. This isn't just a database. It's a dynamic, 3-tiered network that connects rare diseases to every relevant piece of information. Picture it as a layered map. 1. Taxonomy layer, a family tree of diseases, grouping conditions by genetic origins, e.g., mitochondrial disorders, lysosomal storage diseases. 2. Clinical features layer, a web of symptoms, lab results, and imaging findings linked to specific diagnoses. For instance, progressive muscle weakness might connect to 50+ rare conditions. 3. Instance layer, real-world data, case studies, genetic sequences, and clinical trial results that ground the system in reality. What makes this graph revolutionary? It's not static. It dynamically pulls from real-time web searches, integrating the latest peer-reviewed studies and clinical guidelines. Imagine a system that updates itself as new research emerges, ensuring doctors always have the freshest insights. The framework's true power lies in its hybrid architecture. Let's dissect the key innovations. Multi-granularity matching. This isn't just keyword searches. It uses transformer-based models to understand context. For example, if a patient has myopathy with cardiac involvement, the system doesn't just find that phrase. It maps it to related conditions like Duchenne muscular dystrophy or arrhythmogenic right ventricular cardiomyopathy. Concept diversity control. To avoid confirmation bias, the system employs a reinforcement learning component. If multiple algorithms converge on the same diagnosis, it's flagged as high confidence. If they diverge, the system prioritizes rare or novel explanations. Fallback mechanisms. For ultra-rare cases, a 5-level safety net kicks in. This includes 1. Cross-referencing with orphan drug databases. 2. Querying global case registries, e.g. Orphanet. 3. Analyzing genomic variant databases, e.g. ClinVar. 4. Leveraging patient-reported outcomes. 5. Engaging human experts via confidence score threshold. Adaptive sparse control. This ensures efficiency. By pruning irrelevant data paths, the system avoids information overload, maintaining speed without sacrificing accuracy. The results. Let's talk numbers. When tested on real-world clinical data, DeepSeek model, accuracy jumped from 61% to 83%, a 36% improvement. Qwen model, achieved 89% accuracy, surpassing the 90% clinical threshold. BLEU and Rouge scores metrics for text coherence and relevance, saw double-digit gains. But the real win. Expert reviews. Physicians rated the AI's explanations on clarity, reasoning, and safety, averaging 4.55, nearly matching human specialists. This isn't just about faster diagnoses, it's about redefining what's possible. Imagine a rural clinic in India, accessing the same diagnostic tools as a top-tier hospital in Boston. Or a child with a rare genetic disorder getting a precise diagnosis before irreversible damage occurs. The implications are profound. Of course, challenges remain. Scaling this to 7,000+ rare diseases requires continuous data curation. And while the system excels at pattern recognition, it still needs human oversight for nuanced cases. But the progress is undeniable. So next time you hear about AI in healthcare, remember, it's not just about algorithms. It's about turning fragmented knowledge into actionable hope. For millions of patients, this is more than technology, it's a lifeline. Thanks for watching. If you want to stay ahead of the curve on AI breakthroughs, hit subscribe. Until next time, keep questioning, keep learning, and keep pushing the boundaries of what's possible.